we're looking for, when we want to know whether it's a two-prop z-test, you have to decide on the test, because it doesn't say perform a two-proportion z-test. It just says perform a hypothesis test. So what you're looking for is two sample sizes. So we have a survey of 430 randomly chosen adults found that 21% of 222 men, and then 18% of 208 women. So we have two separate sample sizes and two separate proportions. That's what makes it a two-proportion z-test, as opposed to a one-proportion z-test. If they didn't give you this information, if they didn't give you the 222 and just were asking you to compare this sample to the 21% of men, then it would be a one-proportion z-test. So because it's a two-prop z-test, we're going to write our hypotheses. Our null hypothesis is that proportion of men minus the proportion of women equals 0. The null hypothesis is always that the difference equals 0. Okay. It says, is it evidence that men are more likely than women to make online purchases? That tells us what our alternative hypothesis is going to be. It's the probability of, or the proportion for men minus the proportion for women would be greater than 0 if I subtract that direction and I want to know if men are more likely, right? So that would be greater than 0. If I switched it and I did PW minus PM, then it would be less than 0, right? Because we want to know, is PM bigger, right? So then we can set an alpha level of 0.05. And some of the test problems will tell you use a significance level of 0.01 or of 0.1. And if it doesn't, then you use 0.05. That's like the standard. So, don't get creative. Just use 0.05. Okay. And then we have to look at our conditions. The conditions are the same for the one proportion z-test, but we have to check them for both samples. So we have to say that both samples were random, because it says 430 randomly chosen adults. So they did one survey, but then they separated the data. Okay, so both samples are random. And then 222 is less than 10% of all men, and 208 is less than 10% of all women. And then we need to check NP and NQ for both. That's our success failure condition. So this is 0.21 times 222. That needs to be greater than or equal to 10. And 0.79 times 222, greater than or equal to 10. And then we're going to do the 0.18 times 208 and 0.82 times 208. And we need to get those actual numbers. So that gives us 46.62, 175.38, and 37.44, and 170.56. So they're all met. So since conditions are met, a normal model is appropriate. And I will use a 1-2 prop z-test. Okay, so we're either going to do this by hand or in the calculator. Which one do you want to do? Calculator's fine? Okay, this one definitely, the calculator is easier to use, because by hand you have to calculate p-hat pooled, then you have to calculate standard error pooled, and then you have to use that, and it's just a lot more work, right? So in the calculator, let me see if I can figure this. You're allowed to use the calculator on both the FRQs and the multiple choice. So we're going to add in So we're going to insert, let me try this again. Okay, in our calculator, you go to stat, to tests, down to 2-prop z-test. And we did the p hat m first. So we're going to put in here the 222 times 0.21. That was p hat m, right? 0.21 times 222. And then for n1, we're going to put 222. But the problem with the calculator is I cannot use decimals for x1 because I can't have half of a person that shops online, right? So it's either 46 or 47. We'll round it to 47. And then same for the x1, that's 0.18 times 208. Put enter, and again, I can't have 37, so we'll round it to 38, and then 208. It doesn't really matter whether you round up or down. And then our alternative hypothesis is greater than, so that's what we're changing here. We're changing it from less than to greater than or not equal to. So hit enter. And then we enter and calculate. And we get our z-score. Here's our z-score. There's our p-value. This is our p hat 1, right, about 0.21. This is our p hat 2, about 0.18. Why is it not exact? Because we had to round, right? And then our p hat here, this is the p hat pooled. And then there's our sample sizes. Okay, so let's write down. I don't know if that's going to close it. Our z-score is 0.0755, and we're going to write 2-prop z-test. Even though we just said I'm going to use the 2-prop z-test, this indicates that we used our calculator. And then p equals 0.755, and you can write p hat pooled. It's the only thing you don't already have, 0.1977. Okay, but this is our z-score, our test statistic, and this is our p-value from the calculator. I don't know why I just thought of it. Oh yeah, I just wrote down the same thing, huh? That is not the p-value. P-value is 0.225. And so since my p-value, okay, remember we had an alpha of 0.05, my p-value is large, right? I mean, that's bigger than any alpha we would use. So we're going to fail to reject the null hypothesis. So since my p-value of 0.225 is greater than my alpha, I fail to reject the null hypothesis. Right, because the probability of getting this difference is pretty high. There's a 25% chance that just by random sampling variation, we get a difference of 3%, because it was 18 and 21, right? So it's probably not because the genders shop differently. And so there is not enough evidence to convince me that the question said men are more likely than women to make online book purchases. So there's not enough evidence to convince me that men are more likely than women to buy books online. So that's our conclusion. Now our p-value interpretation is a separate sentence. That's if our null hypothesis were 0, right? So if the difference is 0, if the shopping preferences are the same, right? That's our null hypothesis, that men and women shop the same for books online. So if men and women shop the same for books, And that's just me kind of rewording it. I mean, you could totally just say, if there is no difference in the way men and women shop, right? This part is if H naught is true, right? That's the part I'm writing down. And then there is a 0.225 chance of obtaining our sample difference of 0.03. And the 0.03 came from 0.21 minus 0.18. That's our sample differences. P hat M minus P hat W. And that's our conclusion. Okay, so researchers at the National Cancer Institute released results on a study that investigated the effect of weed-killing herbicides on house pets. They examined 827 dogs from homes where an herbicide was used on a regular basis, diagnosing malignant lymphoma in 473 of them. Of the 130 dogs from homes where no herbicides were used, there's 130 dogs, only 19 were found to have lymphoma. So what's the standard error of the difference in the two proportions? Construct the 95% confidence interval. So here we have, again, two sample sizes, right? Two separate samples, and we have successes, so we have two proportions. So P hat with no herbicide is 19 out of 130. And then P hat for herbicide is the 473 out of 827. And let's get those real quick. And 473 out of 8. So this is 0.572. And this is 0.146. And so we want a confidence interval. To do a confidence interval, we have to calculate the standard error of the difference. So we're going to do P hat H minus P hat no H, or NH, because I like my numbers to be positive. I find them easier to interpret. So I'm going to subtract. I can see that P hat H is 57 and P hat NH is 0.1. So I'm going to do this one first, so that's positive. So to do my standard error, it's the square root of P hat H Q hat H over NH plus P hat NH Q hat NH over NNH. So these are the sample sizes on the bottom and your P hat Q hat. So this is going to be, so we're going to do 0.572 and N is 0.827. So 0.572 times 0.428 over 827. And then 0.146 times 0.854 over 130. That's our standard error calculation. We use the actual proportions. And then when we put it on the calculator, we get, and I don't have to put all the parentheses in the calculator. It does the order of operations for us, so it makes it a little bit easier to plug in. So our standard error is 0.0354. So our confidence interval is our sample difference. Let's just move stuff up here. We'll move that up. And we're going to get 0.572 minus 0.146. That's the difference, right? Plus or minus. Times our z star for 95% confident is 1.96 times the standard error, 0.0354. That's the calculation by hand. In the calculator, well, let's find this. 0.572 minus 0.146, and that's 0.426 plus or minus 1.96 times 0.0354, 0.693. This number here is your margin of error. You're going to add and subtract it to the proportion. So plus 0.426, I get 4.495, and .3567 66. So that's our confidence interval. And then to interpret that, we say, I am 95% confident. Now we're talking about dogs getting lymphoma, right? And dogs that have been around an herbicide, right? So we subtracted the herbicide houses minus the non-herbicide houses. So this means that the herbicide houses had a higher rate, right? Because that's how we subtracted it. So I'm 95% confident that dogs, or the proportion of dogs with lymphoma in homes that use herbicide is between, we're going to pretend I just wrote between there, 0.3566 and 0.495 higher than homes that do not use it. And that's our interpretation. Okay. In the calculator, for your x1, n1, x2, and n2, if you're doing that, you're plugging in your 473, and then you're plugging in your 872, your 19, and your 130. You just plug it in like that, and then pick 95% confident.